Welcome everyone. Welcome to the presentation Fast Scalable Universal Approach for Distributed Data Aggregations. My name is Niranda Pereira and I will be presenting this paper on behalf of the following authors. We believe that data science is a formulation of structured data from extraction of structured data from raw data using ETL operations or extract, transform, and load operations. And in the current context, in the current engineering and research domains, artificial intelligence and machine learning workflows have taken over the majority of data science research and uh, enterprise applications. And data engineering is heavily used in both prototyping and in production. A good example of this would be the Facebook's DLRM or deep learning recommendation model, um, which heavily uses data engineering. And data engineering is a complex iterative process that involves a lot of workflows. But if we go a little deeper into the data infrastructure, we could see that only a fraction of real world applications comprised of actual ML code, whereas a lot of other workflows are revolving around data collection, verification, feature extraction, analysis, etc. So those are very important. So without those workflows, you cannot move ahead with an AI or machine learning code, machine learning workflow. So it's very important. So data engineering workflows are very important. And if you look at the modern data science clusters and hardware, we could see that there are GPUs, CPUs, as well as application specific hardware like TPUs and FPGAs, and then specialized networks, as well as commodity cloud infrastructure. And if you look at the trends, we can see that the number of cores and threads are increasing in CPUs, as well as memory is also in the rise uh, with faster clocking speeds, as well as we could also see faster networks and faster GPUs with much more and faster memory. So, uh, if you look at where aggregations fit in all this, is we believe that aggregations are an essential class of operations in data engineering. Most commonly used ones are pure aggregation operations, like simply statistics of a data set. For an example, sum means standard deviation, etc. And additionally, the next set of common operations would be grouping and categorizing, followed by aggregations. So aggregations on groups. So definitely fast aggregations would vastly improve data pre-processing time. A really good example here is the data processing benchmarks like TPC-H, TPC-XBB, where majority of those queries are com comprised of grouping and aggregation. So, and in almost all these applications, there are two main layouts that are being used. One is the table or the data frame layout, and then the array. So the aggregations on each of these layouts would be slightly different. So let's look at it. Um, Tables are the backbone of big data systems, starting off from Hadoop to Apache Spark to Flink. And a table is a heterogeneously typed structured data, and usually aggregations are carried out on columns. And using a columnar data structure may benefit aggregations due to the SIMD parallelization and contiguous memory seeks. On the other hand, arrays and tensors have been the crux of HPC applications in domain sciences as well as AI and machine learning applications now. And they are mostly homogeneously typed and multidimensional data. And the users of these frameworks and the layouts, and users or the parties in data engineering always seek for higher productivity in terms of easy uh, programming, in terms of Python or APIs, and then they would also seek They also seek flexibility and extensibility, where a framework would be able to connect to other frameworks seamlessly without losing any performance. And then next is the performance. So users would seek productivity, flexibility without compromising on performance. And performance also looks at utilizing hardware as efficiently as possible. But we believe that no single system will be able to meet all these demands at once. An example here would be Apache Spark's MLD, the machine learning library, which came up some time back, but uh, it lost the popularity owing to owing to TensorFlow and PyTorch, but still Apache Spark being used heavily for data pre-processing workflows. So uh, there are frameworks which excel in certain domains, and there should be when we design frameworks, we should be seamlessly connect to the each and every framework. That is one of the core requirements. So we believe that a better approach here would be to identify critical areas and then come up with highly optimized libraries and then use them universally with other frameworks. And also, the most critical areas here would be to look at the data storage and then optimize distributed operations, because now the current workflows, data engineering workflows, would may not be able to. Uh, Workflows would require more than one node or more than one core to perform, definitely. And then we would also make maximum use of the network using optimized network communications. So looking at all these, that's where the Cylon came up. It's a fast, scalable, and a distributed table abstraction written on C++ and exposes Python and Java APIs. It's an Apache open source project under the Apache 2 license, and it uses the Apache Arrow format underneath. The idea of Cylon is to bring high performance data engineering everywhere. So we look at uh, we look at Cylon as a universal framework that could connect all these environments, from any data format to any data processing environment to any programming environment, and even for machine learning and deep learning. The architecture of Cylon starts with C++ cross-language interface that exposes uh, language bindings to Python, Java, R, and C++, and it performs it executes on a distributed memory, and it supports data loaders from different data formats, and there would be distributed operations based on certain local operations, and it will also have aggregation. So aggregations and group by operations would also fall under the distributed operation. And it will also have optimized network operators and the communication layers. So if you look at the aggregations in Cylon, there are two main categories, like I said earlier. So we look at aggregation operations as well as group by operations followed by aggregations. So it's provided under the Cylon Compute API, and it's implemented in five stages, where we first identify the internal states depending on the moment of statistic, first moment, second moment, goes on. And then uh, in a particular, so since we are using arrow format, we would be looking at columns in arrow arrays. So arrow arrays would be chunked, so we would be doing a bulk aggregation on chunks, and then bulk aggregation into an intermediate result, and then uh, merge these results into a local intermediate result, and then do a communication operation to come up with an global intermediate result, and then convert it into a final format. An example here would be distributed mean calculation done by sum and count individually, and then yeah. Next, let's look at the group by operation. It's semantically similar to the MapReduce abstraction in Hadoop. There are two approaches mainly. One is hash-based approach, and then another one is the pipeline-based approach. Another concept in the group by operations would be the early aggregations, where we incrementally build up the grouped aggregation. This is very similar to the element-wise aggregation step we discussed earlier, and it reduces memory footprint and communication overhead. And this has been used in hash-based group in Cylon, and we will discuss more about this in the experiments. Group Another concept is how group by implemented in certain frameworks like Python Pandas or Spark, where they uh, separate out group by and aggregations. But this could lead to poor cache performance due to random memory reads across the indices. Whereas in traditional SQL, group bys are always provided with aggregations, and this allows the early aggregation optimizations. And then we also have to look at the effect of the local combiner step for distributed operations. It may reduce communication overhead, but it depends on the number of rows and the unique groups. If they are relatively similar, the local combiner step actually reduces performance, and we'll see that later on. Pipeline group by is a term coined by the Vertica column database, and it's usually applied on sorted tables because sorted tables relaxes the restrictions on groups, and it significantly reduces memory footprint, and it supports trivial multi-threading as well. So let's look at the experiments. So we are looking at Xeon 8160 processors, and we increase the process. We look at the maximum processors. For this paper, we've used 160 processors. We are using Cylon with GCC 8.2, OpenMPI 4, and comparing with Apache Spark 2.4.6. And we look at the tables from 200 million rows up to 1 billion rows. And firstly, it's the scalability of aggregations. And as expected, we would expect a linear scaling, and Cylon shows almost perfect linear scaling and up to a speed up of about 27 times against Apache Spark. We would like to improve on group by and followed by aggregations, because currently, even though it shows good, it shows decent uh, strong scaling. Um, uh, the worst case scenario of group buys here, the number of rows here is 1 billion, and unique groups here is about 990 million. So this is like a worst case scenario for group by operation. Um, we would like to improve on the speed up against Spark, and we are working on it now. Next up, we'll look at the effect of the local combiner versus the group size. And here we are looking at 200 million uh, rows where we are changing the average duplicate rows per key from 1 to 10,000. As we could see, the average when the average increases, the total time reduces as expected. And with the combiner, this effect is much more prominent because we would be first locally combining the result and then do a shuffling and then do another local operation. So if there is sufficient duplication, the local combiner significantly reduces the total execution time. Ah, yes, and then we'll look at the pipeline group by implementation. So we are looking at 200 million rows locally sorted, and we are comparing this with the hash group by implementation. This also pipeline group by also heavily depends on the number of average rows per group. So as the n divided by g increases, the pipeline group by becomes more effective. As you could see, we are looking at 10,000 here. The green line is 10,000, and the blue line is just one, on average 1.01 per group, rows per group. So pipeline group by gets adversely affected by the lack of work per group, and we are looking at formalizing a model to switch between hash and pipeline group by, and that comes as a future um, improvement. And because Cylon looks at universally universe as a framework that universally connects to other frameworks, we it's very imperative that Silence should be able to seamlessly switch between runtimes. So if you look at C++, Python, and Java bindings these results are given for inner join performance. And as you could see, the overheads are negligible between these these bindings. So in conclusion, Silent provides a fast and scalable backend for aggregation operations, and it also creates a universal bridge by seamlessly integrating with other frameworks. It also allows data aggregation to take advantage from both big data and HPC worlds. That is our main idea. And then it also achieves superior performance and scalability than the state of the art big data systems. As per the future improvements, Cylon is still at very early stages of development, and we are looking at cache and NUMA-aware optimizations for computation kernels, including aggregations. And we look at unifying Cylon compute and group by APIs, and to provide a pandas like distributed data frame abstractions because of the popularity and user friendliness of pandas. And we also want to support disk-based operations and to expand more on other data formats. In summary, Cylon is a fast, scalable, distributed in-memory table that enables high-performance data engineering everywhere. That's our final goal, and can be used as a standalone framework or as a library. And the trivial overheads when switching between Python, Java, and C++ allows it to be used anywhere without losing performance. Thank you very much, and I'm open for any questions.